Okay? All right. So welcome to the last class. This is amazing. It's amazing to me. I'm sure it's amazing to you. So before we start lecture, as you know, we have a couple things coming up after the last class. The poster session is Tuesday. And the final exam is then Friday, a week from Friday. And check out the website just to make the class website just to make sure you know exactly where and when those things are. The final exam will be, as the midterm was, open book, open notes, closed computer, closed cell phone. And you won't need a calculator, as far as I can tell, for the final exam. But you will need your brain and full understanding of material. So, and I think maybe what we'll do is, for the poster session, I think just consult the instructions that are on the website if you have any questions about. And, you know, if you don't know how to print out one huge page, it's okay. You will not be penalized any points if you print out 8.5 by 11 pages and staple them on the thing. That's just fine. Also, one quick announcement, though. We would like you, when you turn in your final project reports, to turn in hard copy as well as sending us an email copy. It just makes grading a lot easier if we can get a hard copy from you. One student sent an email and said, but I'm going to be in some other geographic region at that time. Do I have to rush home or mail or FedEx you a hard copy? No. Just send us an email that says in bold letters in the title of the email, I'm the one who is out of town, and so please print this out. The one who is out. Okay, so today let's finish up Markov decision processes and also spend a little bit of time studying for the final. That's the goal. So we talked about Markov decision processes last time. Here's the picture that is easy to carry around in your head for that. The red part is just our old familiar hidden Markov models. The blue part is, well, the full picture is a partially observable Markov decision process, assuming that we can't really observe the state directly, but only observe the outputs the same way we would in a hidden Markov model. If, in fact, we can observe those states, like here, if we do observe the states, then this portion of it we just call a Markov decision process. Okay, so we talked about this last time. And we talked about the formalization of our problem is to learn this policy function, pi, the green function that looks at the current state and chooses an action. And which action do we want to choose? Well, we agreed we would try to learn to choose the action that maximizes the sum of expected future rewards, discounted exponentially into the future. So I'm sure you recall that. And so, in fact, we ended up noticing that we could take that expected sum of future discounted rewards as the value of some evaluation function. We'll call it V star. The value of any given state, we could say V star is just the sum of expected discounted future rewards we'll receive if we happen to start in that state, and then do the sequence of optimal actions starting in that state. And we'll call that the value of the state, because it captures our intuitive notion of how good it is to be in state 1 versus state 2 is we'd rather be in the state that has a higher expected sum of future rewards. And so if we can learn that evaluation function V, then we can use it together with our ability to predict what the next state will be if we do an action. Then we can use our evaluation function V together with the ability to predict what state we'll end up in if we do action 1 versus 2 to choose whether we'd like to take action 1 or 2. But then we mentioned that if we don't know the next state function, if we're a robot and we really don't have a perfect ability to predict what will be the next state I'm in if I execute action 74, then we need something other than V, because we can't do the one state look ahead because we don't know how to predict where we'll be if we do action 73. And so then we noticed, well, instead of learning the evaluation function V, we could learn the evaluation function Q, which is just like V, except that we define it over state action pairs. And now instead of choosing actions by saying, let me simulate going forward one step and see what the value of this state will be, instead I just say, would I like which Q value is higher? The Q value for the state action pair consisting of my current state, which obviously I can observe, and action 1, or the Q value of my current state in action 2. So basically we just defined a similar but slightly different evaluation function, Q, that has this nice property that we don't even have to do a one-step look ahead. We just look at our current state, and then we look up in our Q function whether there's a higher value for action 1 or action 2 in the current state. Okay, so that's where we left things. And we also talked about an algorithm for learning both V and Q, and the algorithms were remarkably similar. They basically operated off the following insight. We can, well, first of all, we observed that in a lot of these cases, if we really knew the next state function, we could just do dynamic programming to take a world where we knew where the rewards were and calculate the V value for each state with dynamic programming, kind of working back from the states that, from where the rewards, the immediate rewards were, to figure out what would be the expected discounted value one step away from there, and then 2 steps away, and then 3. And then we pointed out that, well, instead of doing a full dynamic programming thing, we can just sample the state action pairs. And if we do, and we apply a simple update rule, then randomly sampling state action pairs, and doing that long enough, will give us the same result as dynamic programming. And so we zeroed in on this kind of update rule, which said, well, suppose we have a robot in some particular state, and it decides to do a particular action which lands it in some other state. Then that robot just sampled the state action pair, the state it was in, the action it did. And we, as we said, the Q learning algorithm essentially just says whenever you do that, then if this is the Q hat value for the state action pair that we just sampled, then what we'll do is after we sample it, we can replace our old estimate for what Q hat is for that state action pair. We can replace it by a better estimate. How do we get that better estimate? Well, we just take the observed reward that we actually got when we sampled a state action pair, in this case a reward of 0, immediate reward of 0, plus the discount factor times the maximum over the outgoing actions we could take from our new state. Right? And in fact, as we noticed, that maximum is, in fact, the V function for the new state. Okay. All right, and so learning the V function through value iteration and learning the Q function this way, both are basically using the same idea. Where every time if we have some estimate of what V is or some estimate of what Q is, every time we take a step, we can improve our estimate for the state or the state action pair we just left. Because now we're in a new state where we see more stuff. Maybe we just got a reward too, in which case now we know a lot more confidently about what the value was of being in that state. But even if we don't get a reward, well, now we can see from this new state what are the outgoing actions and what are their values. So that's the key insight in how we do this. Yes?
Were the outgoing values of the second state estimates themselves?
For the
second state, the outgoing values are themselves estimates?
Yes, yes. So the idea is that all of these numbers that I have here are my current evaluation function. And so what I'm doing is I'm using the maximum over the actions of my estimate for Q. I'm saying, well, it's sort of like this. It's like, I think my estimate's going to be better the closer I get to the goal. That's one way to think of it. Right? So, in fact, that's what this little stuff down at the bottom of the page is about. Think about the following thing. Remember we had our goal state here? In our immediate reward, I'll draw immediate rewards in green to distinguish them from the black Q estimates. But remember we had this little thing here where our immediate reward for staying in the goal state was 0, but our reward for getting into the goal state was 100. And so now imagine executing this algorithm where we first initialize all of our Q hat values to 0. Okay, and now if they're all initially 0, they won't be these numbers like 72 that I have here. They'll be all zeros, all my Q hat estimates. And now when the robot takes that step, all the zeros, well, they'll remain 0. Right? Because when it applies this update rule, it observed a reward of 0, plus now it's going to take the max of all the outgoing actions. Well, they're all 0 anyway. So that's going to stay 0. But then if it happens to continue east, it will stumble upon the goal state and get a reward, an R, an immediate reward of 100. And then when it applies this same update rule, it will suddenly have a Q value that's non-zero here. It'll get 100 there. Why? Because the immediate reward was 100, and so that update rule will update that one Q value. But now, if it happens to be reborn, I guess since we have a terminal goal state here, we need reincarnation for the robot. So if it gets reborn in a different random state and starts wandering around, the next time it wanders into this square, this update rule will then be the maximum of all the outgoing estimates, which in that case are going to be 0, 0, and 100. And so now, bingo, it'll have a chance to update the state action, the Q value estimate for the state action pair that led it into this state. And so you see, every time it happens to find itself in a state for which it has one of those non-zero Q values, it's going to be able to update the state action pair value that just got it here. And so over time, you know, if we look down from the sky on this grid in the evolution of those numbers, what we'd see is non-zero numbers propagating out slowly over time away from the goal state. And if we waited long enough, they would just stabilize to the Q values. And so, and all along the way, we'd see the estimate after n+1 training steps is at least as high as it was. They all started out at 0, and they're just monotonically increasing or staying the same. They're non-decreasing over time. And at any given time, if we just stop and ask, the estimate of the Q value will be bounded by 0 and the actual unknown to the robot true Q value. And so you see what's going to happen is this, over time, Q hash is just going to get closer and closer to Q, and eventually it will get there. Yeah?
Why doesn't the information propagate past the... So we just found you made a series of actions, and you found the goal. And you just got rewarded 100 points.
Right.
Whatever. And why doesn't that propagate all the way back to your start state?
Yeah, great, great. So the question is, why doesn't that information of where the goal is propagate further than just one step? And the answer is because this is not a very sophisticated learning algorithm. And we'll get to something called TD lambda in 2 slides, which does a further kind of propagation. Okay? So before we get to that, let's think about the non-deterministic case. So that example we were just going through and the Q learning algorithm we talked about was really for a deterministic world where if I take the same action from the same state several times, I always get the same result. Deterministic next state function. If it's non-deterministic, then that update rule that we said is not actually going to converge in general. Because, imagine that if I take this action with probability 0.9, I get 100 points, and I end up there. With probability 1 minus 0.9, I get minus 100 points, and I end up there. That kind of non-deterministic world. I jump over the cliff, and either I make it, now I'm on the good side, or I miss. And so if that's non-deterministic, and if I keep sampling that, then, some of the time I'll end up this way, sometimes I'll be that way. And if I overwrite the Q value for that action each time, it's not going to stabilize. It's just going to bounce back and forth between thinking that I'm going to get 100 points or that I'm going to get minus 100 points. So it won't really stabilize. So to deal with non-deterministic worlds, we can't quite use just our old update rule from the previous slide. What we really want to do is blend in that recommended update from the new state action pair that we just sampled. We want to blend that in with our current Q value estimate. So here, the subscript n is the nth training step. And so what we want to really do is, our old rule was essentially on the nth training step, make the Q value for state action pair SA the observed reward plus the maximum over next states, which you get here. Now we want to actually blend that using blending coefficient alpha, which is between 0 and 1, with the value we already thought we had. So if we do that, then you can see if we keep sampling the state action pair, and if alpha is small enough, then we're going to do just fine. We're going to end up with an average of the outcomes of those samples. Now, how small do we need to make alpha? Well, here's a good recipe that converges. If we make alpha on the nth training step a function of how many training steps we've already seen, then basically we just decay alpha. So when we're to the 1 gazillionth training step, that training step has less influence on updating our Q value than the first one. And so this way, that random outcome that we're going to get from sampling the state action pair, its influence decays over time. We rely more on the average that we've gotten over time. Okay, so I think intuitively you can see why this might converge. It does, in fact, converge. Last time we proved convergence for the deterministic case. That proof can be extended to the non-deterministic case. But I think this gives you the intuition of why and how.
On the previous slide, there was a condition saying that the reward is non-negative. So what is the use of that? Even in the proof of last class, I don't remember using that condition.
Yeah, the question is, do we need the constraint that the reward be non-negative? It doesn't seem to me that we need that, but say that again?
Is it there to prevent keeping your opinion?
Short answer, I don't know. these statements clearly apply if the rewards are non-negative. If you have negative rewards, then this one, for example, won't be true.
But it's not obvious why this is true for non-negative rewards. You need to do some proof.
Yeah, this is true for non-negative rewards. It won't be true if we have negative rewards. What's not clear is that whether this needs to be true in order to prove convergence. So short answer, I don't know if you need it to prove convergence. Okay, so I want to come back to the question that was asked over here earlier about, well, isn't it kind of a really stupid algorithm to take this long path? You know, we start out with the Q values being 0 everywhere, and we take the robot wanders around for 15 steps and finally stumbles on a non-zero immediate reward. And now our algorithm just updates one Q value estimate for one state action pair, the one we just took. Why don't we at least say, well, let's update this Q value also for 2 steps before we got here? Now that we know that we're going to get a reward, we're sure the Q value there isn't 0. Why don't we just update it? So temporal difference learning is that idea. And in fact, something called TD Lambda is exactly that idea. And the idea is this. So here's the training rule that we used before. We said we're going to replace our Q estimate with a one-step look ahead. Estimate. And what I mean is, you know, we go ahead and take action A and state T, we get a reward, and then on the one step ahead state, we look at the Q value and we update just one step into the past. But what we could do is we could do 2 steps. Right? We could say, well, we're in state T, we took an action, we got some reward, we took another action, we get another reward, and now we have an estimate from that new state we're in also of how good that is. It's the maximum over its things. So why don't we update the Q value for the state at time T based on those 2 steps plus our estimate at state T plus 2. And we could. It's a reasonable thing to do, and it would allow us to propagate those things back further. Or n steps. We have to stop at 2. And in fact, we can do them all. So we can blend them all. If we say this is our Q1 update, the 1 step ahead update, here's a 2 step ahead update. What we could do is we could say, well, we're going to do them all, and we're just going to blend them. So now imagine this. You know, I'm in state, let's call it ST. I go 1 step ahead. I get a reward. Oh, I get my Q1 update, so I can go ahead and update that first action pair's Q value. Now I take another one. I get another reward, and I look here, and I see what my outgoing actions are, and I get the max of the Q values for that. Well, I can update the previous one, but also that one 2 ahead, 2 behind. And that's the Q2 update. Now I get to the third one, I can do the Q3 update on that very first step. And in fact, I can blend them. And if I blend them this way, we get an algorithm called TD Lambda, which in fact also converges. And that's actually, in practical terms, a more a lower sample complexity way of learning the evaluation function. So we get more information out of each state action pair because we're using it to update now actually our infinite history of state action pairs, our infinite history of those get their Q values updated when we take a new step. Now think about that just for 1 second. How dangerous is it to update the Q value 100 steps before I got here based on this new reward? It seems more dangerous than updating the one that just got me here. I'm sure that that thing is going to get this reward. But if 100 steps ago, I wasn't even following an optimal policy, I'm just trying to learn stuff. So really, you know, it's not guaranteed that the Q value there should be this particular discounted future reward. It should be at least that, but probably it should, if we have non-negative rewards, but probably it should be, there's a good chance there's a more optimal thing to do from there, and its Q value should actually be higher than I'm saying. And for that reason, the intuition is we want to have a smaller influence when we see some reward on the Q values for 100 steps in the past than for 1 step in the past. And that's where the lambda comes in. It's essentially discounting t steps in the past. I discount by lambda to the t. But I still have some influence. And so that's the intuition behind TD lambda. And in fact, it does converge. We won't go through the proof of it, but you can kind of intuitively see why it's a reasonable thing to be doing. Okay. Yes? And then
so by doing T gamma, are we still following the Markov assumption?
good question. So when we do this algorithm, are we still assuming making the Markov assumption? Yes, we are. So yes, we are. We're saying that the reward and the next state function depend only on the immediate state and not how we got here. But within a world that obeys that Markov assumption, of course, what we're trying to do is learn a good control strategy. And the reward that in fact we'll achieve, whether the world is Markov or not, the reward we'll receive in the future, discounted future reward, is a function of the entire sequence of actions we choose. But when we say we're making the Markov assumption, what we're meaning is that the reward itself that we receive is only a function of the current state action. And the outcome of an action is only a function of the current state. So there's a difference between the assumption, the Markov assumption, which is really about what do immediate rewards and next states depend on, versus our control strategy that we're learning, which of course the value V star depends on the entire state space that we're searching. Yes?
Could you go back 2 slides? I think there's something here that was confusing. So in this equation, the max q hat n minus 1,
Mm-hmm.
is that the previous state?
Oh, let's see. No. So n here is the nth training step. And so what I'm saying is that I'm going to, after each training step, I have a new q hat function. I'll call it qn after n training steps. And all I'm saying is here is that I'm using the q hat function I have it after n minus 1 steps. I'm using that function to update the q hat that I'll have after the nth training step. But the states themselves are different, right? This is the state we were in. This is the state we're now in. Or I guess I said that backward. This is the one we end up in. This is the one we started in. Okay. Okay, so there's the idea. So TD lambda is just this algorithm. It has a nice property that it converges. And in fact, it's often a more practical algorithm because it converges faster. It spreads the information out over more steps. And that's why when Jerry Tesoro did his reinforcement learning version of backgammon playing, he used this algorithm. Okay, so let's end this by summarizing. So here are the main points of Markov decision processes in reinforcement learning. So you should know about the model we're talking about. And then we really talked about, I think, 2 key algorithms. The first one was when we made the assumption that, well, what if the robot itself that's trying to learn this control strategy actually knows the next state function for the world? Like if you're playing chess, you know the legal moves of the game. You don't know the strategy, but at least you know the legal moves. And then we saw that we could learn this value function v. We talked about value iteration as one way of effectively doing a sampling version of dynamic programming. But then the second condition we talked about was, well, what if we don't know that next state function? We don't know perfectly what state we'll end up in if we do a particular action, which is the case for most robots, sadly. And so then the kind of surprisingly pleasant fact is Q-learning works in that case. So despite the fact that the robot doesn't actually know what the next state function is, and in some sense doesn't have to learn it, it can still, just by wandering around through the world, sample state action pairs in the real world and learn the Q function eventually. Now you might think, given that, why don't we have the robot, while it's roaming around the world, also go ahead and learn the next state function? And people have looked at that. That's a very reasonable thing to try to do. And then you might imagine, well, if the robot did start to learn an approximation to the next state function, then it should be able to somehow get even more information out of that. And that's an interesting research topic that's still a little open-ended. Uh-huh.
So like this robot roaming around not knowing what to state, and it's gonna hurt itself very badly, right? It's gonna go there.
Yeah.
What do people do, I guess?
Yeah. So the point is, well, robots roaming around can hurt themselves very easily. It's true. And this algorithm and our analysis of it ignores that possibility. In practice, people do use these kind of algorithms. For example, we started by talking about a helicopter flying reinforcement learning. You can only imagine how bad that could be. So to make that work, what people typically do is constrain the actions that the robot can choose in various ways. So one is you could put, if I really didn't want my robot to collide with things, I could have it choose actions, but I could have a proximity sensor that just refuses to keep going if I'm within an inch of a collision or a foot of a collision. And now the robot still chooses to go 1 meter ahead, but the very definition of that action is now different. The action is to execute the action of trying to go 1 meter ahead, subject to the constraint that the proximity sensor is going to put you in some other unexpected state if that's impossible. So one way is just to put a whole set of lower level bumper guards, so to speak, on the robot. Another is to put priors. Obviously it'd be nice. Another is to have robots teleoperated. That's actually an important point. So there's nothing about this algorithm that we've talked about that says the robot has to choose the state action pairs. All the robot has to do is traverse some trajectory of state action pairs. That could come from a human joysticking the robot, controlling it, driving it down the road, flying it in a model helicopter. And that same sequence of state action pairs could be used with the same algorithm. So that's another way, is to actually have people drive the robot, so to speak. But I would say it's another one of these kind of unsolved issues and important issues. And why did we even ignore it? Well, we ignored it because we wanted to get to the essence of the algorithm and be able to prove some convergence properties. But in practice, it's key. Okay, so any other comments, questions? Yes?
So, would it be reasonable to think, like, once you reach your goal state, is seeing that as because this sounds very similar to gradient ascent type, from a conceptual point of view, to assume that as like a point, a peak in some graph, and then estimate the whole topology based off some type of function, where you made a kind of an estimate of the whole topology based on the particular
Oh, you're talking about estimating the topology of the state space based on the trajectories? Yeah, I put that under the category, I think, of trying to learn the next state function while you go, right? Knowing the topology of the state space is related to knowing at least some constraints on the next state function. Yeah?
So in the TD lambda algorithm, so every time you take an action, you use the reward of that step to update the queues several steps back, right?
Mm-hmm.
So it's like there's a trade-off between the time you spend on every step and the learning rate.
Yes, good point. So there, right, picking the parameter for the TD, I'm forgetting whether that was a gamma or a lambda, but picking the parameter.
It's not lambda, it's like how many steps do you propagate with that?
Right, right, it's this one. It's the, it's,
Oh, no.
no,
It's not there. It's like implicitly you assume that you
It's
are
this one.
propagating it all the way back.
right. So this, this exponent here is the thing that's determining how strongly I influence things at a given point back in the history. Picking that parameter actually is engineering choice. But the interesting thing is that you do get convergence as long as you pick that between 0 and 1.
Yeah, but what I mean is that in this formula, you assume that you are propagating it all the way to the birth of the robot. Because
Yes, yes,
yeah.
exactly. This is going back to the
Actually,
infinite past.
If the game takes like 1,000 moves.
Yes, of course. If the trajectory is 1,000,000 steps long, then you will hit underflow issues eventually, and you should stop. And in fact, maybe it's not even worth the, as an efficiency hit doing that. In the end, it kind of comes down to how costly is it to actually take another step in the world compared to how costly is it to do some CPU cycles. And so there's a trade-off there too. Yep.
So if you have a state space and you know so this is useful if you don't know the whole whatever it is. So you can't actually search for it.
Uh-huh.
So or use dynamic programming. So if you do know it, but it's too big to actually do dynamic programming, does this help or does it?
Yeah. So that's a good point. So in fact, this is also a way of trying to attack dynamic programming problems that are too big to do. So it's a kind of sampling strategy. To make it work in practice as a replacement for dynamic programming on large-scale problems is very difficult. And the reason is there's a sense in which here we're really doing rote learning, right? We're not really generalizing across states of the world. We're just saying, well, we were in state 74 and now we took action 17, and so state 74, action 17 will update its thing. But we won't say, well, that's very similar to state 73. We don't generalize across states. And in fact, our convergence proof relied on us having just this big table for every state action pair, a different value. So if we really have a problem that's too big to run dynamic programming on, that Q table is going to be huge also. And since we're only updating the actual state action pairs we visit, we're going to have to sample an awful lot before we even get all those values to be non-zero. And so that raises another interesting research question, which is, well, why don't we, instead of plunking those Q values into a table, why don't we use them as training data for some regression function, like a neural network? Why don't we just say, the robot perceives these pixels, we'll call that the state description, and we'll train a neural network to predict from the pixels it perceives what is the V value for this. And then we could use our updates to train that neural network. And in fact, you can do that, but it ruins the convergence proof. And worse than that, it ruins convergence in practice in many cases. So the last line of this little story is, it turns out you can identify certain replacements for the neural network that do generalize across states, for which the convergence can be proven still. even though it doesn't work for neural networks. For example, if instead of neural networks I use nearest neighbor regression, I take the k nearest neighbors weighted by the distance from this pixel pattern and take the mean of those. That actually works. So that's a different way of generalizing across states. But that one works, and the convergence proof can still be proven. What's the difference? The difference is that when you train k nearest neighbor, the Q estimate you're going to get if you take a weighted average of your neighbors is bounded from above and below by their Q values. And if you use a neural network, there is no bound. You're tuning these parameters in this global approximation called the neural network. And every time if I'm over in this state and tune a parameter of the neural network, it's going to change the Q values for every state that I'm around. And it turns out that difference is responsible for whether you can use the neural net function approximator to do as the basis for representing your Q function? No. Versus nearest neighbor? Yes. So actually it gets to be a pretty interesting interaction between function approximation strategy and this sequential kind of training that we do in MDPs. So it's a pretty rich problem, and you can see that if you did that kind of function approximation, maybe you could come back to your idea about using this as an efficient way of replacing dynamic programming in huge problems. Okay, so I want to move along a little here because I want to also mention something which I find fascinating, which is that this particular algorithm turns out to be the best computational model available for explaining certain neural phenomena in animals. So let me show you what I mean. Here's a pretty well-known paper in certain circles, which now dates back to 1997, where somebody had a monkey, and they were doing experiments on the monkey to see how it behaved while it was learning to anticipate future rewards. And here's the experiment. They had a probe in the monkey's brain, so they're recording spiking from this neuron in the monkey. And what they did was they would record over time spiking in the monkey, and each row here is one time trajectory. And the dots are the spikes of the neuron. So you can see there's, and this top row is just a histogram summing up all the dots below in the different trajectories. So you see there's this one point in time around here where there was a lot of spiking going on average. And that's because at the time point labeled R, the monkey received sugar on its tongue. So the monkey's sitting there recording from the cell, the neuron in the monkey. Sugar appears on the monkey's tongue. That's aligned with R. Now you can see there's additional spiking here. So the question is, what's going on with this neuron? Maybe this is a neuron that's actually observing the reward. Maybe it's the sugar tasting neuron in the monkey. Okay, that's one hypothesis. But now, what if we take that same monkey and a second before we give the sugar, we flash a light? Then eventually the monkey will learn to associate the flash of a light with this upcoming reward. And if you do that, sure enough, the monkey, monkeys can't talk that well. So we won't say what the monkey knows, but here's what we observe. So CS is the conditioned stimulus. That's the light flash. And R is the time when the sugar appears. Same neuron. So now what's interesting is after the monkey learns that the light precedes the reward, that neuron no longer fires particularly intensely when the sugar appears. Instead, it's firing when the light appears. So I guess that neuron's not the sugar tasting neuron. Maybe it's the, gee, I just got some reward, or gee, I'm about to get some reward neuron. Okay, so let's probe further. Now that the monkey has learned this, what if we blink the light, monkey's anticipating a second later the sugar, and we withhold the sugar? This is what happens. Okay, so here's the light. The neuron fires. No sugar. Whoa, there's depressed firing when there's no sugar. So what's the explanation for this neuron? What's a model that would explain this behavior? You know the model. We could say this spiking rate that we observe in all three situations could be explained with a single idea that this neuron is coding the discrepancy between the expected future reward at time t, the expected sum of future rewards at time t, and the expected future rewards at time t plus 1 plus the one we just got. It's the error signal in the reinforcement learning that we've been doing. So let's look at it this way. This way. Good. So it's actually explained by exactly this. So you can think of the reward plus discount factor times the estimated value of being in state t plus 1 minus the estimated value that we had at for state t. So this is basically the error signal that we use in our reinforcement learning algorithms for V and for Q. Well, for V in particular, to update our V table. That explains what's going on. So think of the first one. The first panel up at the top, the monkey doesn't know that sugar's coming. It's just sitting there waiting, then bang, sugar comes. Wow, that's good. So the state right before that, it should be anticipating, well, you know, eventually, on average, I get some reward, and then bang, here it is. Oh, so there's a surprise. Right at time t, it had a rather low expectation for its discounted sum of future rewards. But now at t plus 1, it has the same low expectation for the future, but that plus the observed reward that it just received is the signal it should use to update the state right before it received. And that's what this signal is. And that's, we could say that's what the histogram on the top panel is. Similarly, the second one's the same thing, right? Now the monkey has learned to expect a second in the future after it sees the light that it'll get the reward. So at that point, let's think again about t being right before the sugar comes. Now the monkey has learned the sugar's just about here because it just saw the light, and it knows that that means the sugar is 1 second later, and here the clock is ticking down. So it's anticipating the reward. It gets the sugar, got the reward as expected. Its estimate was correct. It was expecting a lot of reward. It got a reward, and now it's in the state where it's not particularly expecting any more reward. The error signal is small. It's learned it. And then here, what we're seeing is the same thing we saw. Well, here it didn't know the light was going to blink. And so when the light blinks, all of a sudden, its expectation about future discounted reward just skyrockets because it's expecting now within a second it's going to get sugar. So this actually is a very good model for all three of those. And it's hard to come up with anything else that is. So this is a very interesting example of where a good engineering machine learning algorithm happens to be arguably the current best explanation for the kind of firing that we see in this kind of cell. So people have been quite interested in this, and more recently started studying. The next obvious questions is, well, is that how us people work too? So us people don't like having electrodes stuck in our brain. So, but now we have fMRI and other brain imaging methods. We can do similar experiments. So here's an experiment done more recently where people were subjected to trials of 4 types. And here's a little diagram off on the left that kind of shows what the possible trials are. So a trial consists of starting on the left side of this diagram and going to the right. So you might get, you're sitting there in the brain scanner, and an A might appear on the screen. You got QA. And now after that, with some probability, you'll get QB, a high probability, you'll get QB. And with a low probability, you'll get QD. So you get an A. Now you're thinking, might get B, I might get D. After you've learned, you're thinking this. At first, you don't know it. If you get QB, then the next thing's going to happen is a lot of pain. And if you get QD, it's only going to be a little bit of pain. On the other hand, if you start in QC with high probability, you're going to end up in QD and get the low pain. But with lower probability, you might get QB, and that's going to be high pain. All right, so volunteers participate in this experiment. And of course, they don't know the probabilities the way you and I know them of what's going to happen. They're just lying in the scanner watching these cues appear and getting little or lots of pain. And eventually they learn what's going on, and by self-reports they know that QB is a bad thing to see. Okay, so now, but the thing is, while they're learning that in the scanner, their brains are being imaged. And so what we could do, and what these guys did, is let's go back to that monkey result where we saw that the error signal that we use to update our V function, the difference between what we initially think the value of the state is and what we now think we should have thought it was worth, now that we observe this plus or minus reward plus have our expectations going forward, that training error signal. Let's ask what would that training error signal look like over time if we had a reinforcement learning algorithm learn this. And then let's look and see if anywhere in the brain of these people follows that, behaves the way that training signal does. And so here are, the solid line here shows for each of these 4 types of trials, which have their own probabilities, you can see what they are. For each of these 4 kinds of trials, once you had learned, the solid line shows what the error signals would be. The error signals are still not 0 even after you've optimally learned what's going on, because you don't know when QA is going to appear. And then you also don't know exactly whether it's going to be QB or D that you get next. And so there's going to be some surprise as events unfold. That's what the solid line is. And then the dotted lines on the top one show what those signals would be initially before you had learned it, and then midway through learning. Okay, so you get the idea. We could actually run our reinforcement learning algorithm on this stimulus, plot out what those error signals are, and then we can just look and see, is there anywhere in the brain that correlates with the predicted error signals? And here are the locations in the brain that correlate with that. We won't go into brain anatomy here, but as you can see, there are these interesting locations where the brain activity correlates with that error signal that our reinforcement learning algorithm gets. And so here's some evidence that this kind of learning about future rewards in this case, in a passive way. You're not actually choosing actions. You just passively, it's a Markov process, but it's not a Markov decision process. You don't have any decision to make. But in this case, here's evidence that human brains are exhibiting neural behavior that is to some degree predicted by this kind of learning algorithm. So I just find this fascinating. And in general, as I think about the future of machine learning and where the field is headed, think out 5 years, 15 years, 30 years from now, we're going to know a lot more about the human brain than we know now. Hopefully we'll know more about machine learning than we know now. And in a way, it kind of makes sense that you and I, in some sense, have to abide by the same information theoretic constraints that our machine learning algorithms have to abide by, at least if you're a materialist. And so it should be that any fundamental laws that we discover about machine learning ought to, it's not like just because we're humans we're allowed to violate those laws. So I think it's kind of interesting to think about what, if you wanted to understand how humans learn, I think there's an interesting opportunity for combining psychological studies and brain imaging studies of people, but also trying to build computational models of what is that learning algorithm that our own brains are using. And so this is one of my, I've looked long and hard for examples where machine learning intersects with studies of human learning. I've been working on a draft paper whose title is Human Learning and Machine Learning for about 6 years now, and it's about this thick. So there isn't a lot out there, but this is one of my favorite examples of where there is a genuine overlap. Okay, so that's what I really wanted to say. Of course, this is not a perfect model of human learning, and it only covers a particular type of phenomena. There's much more to be known. But it's kind of an interesting connection between this engineering approach and what we see in neural systems. Okay, so any other comments, questions on this? Otherwise, I want to spend a little bit of time looking at topics for the final. Okay, let's do that. So when we are making up the final, I thought it would be handy to start, and I sent you all an email about this, by just making a list of what I thought were the most core ideas that we learned in the course. And here's the list I came up with, the same one I sent you. But I thought it would be worth just spending a few minutes going through this list together, and as we go through it, feel free to ask questions. And I made up this list not by looking at the lecture schedule, because I didn't want to be trapped into thinking, well, we did this, then we did this, we did this. I just sat back looking at nothing and just said, well, what's important about what we've learned? Okay, so I think here's the list I came up with, and as we're making up the final, we have this list in our mind, so I thought it would be helpful to share. Okay, so this also kind of shows how far we've come. So if you think back on the semester, what is learning? On day one, we said, well, learning is getting computer programs to improve some performance at some task through some kind of experience. But now at the end of the semester, we all see that very much of what we talked about was really function approximation of different types of functions from different types of experience. Mostly the experience that we looked at was supervised labeled xy pairs for the function that maps from x to y. We also looked at some unlabeled example kind of experience, just x's without the y's. And in the MDP stuff, the reinforcement learning work, we're looking at this idea of delayed reward kind of experience. When we did when Burr did the guest lecture on active learning, it was yet a different kind of experience. It was the experience where the robot gets to pick the X and then ask the Oracle teacher for the corresponding Y, which is, for example, quite different from when we talked about the type of experience that we talked about when we discussed pack learning, which was that we just randomly sample some X from P of X, and then we get the label from the Oracle teacher, as opposed to the learner actively choosing which one it wants the label for. So in the end, we ended up discussing a variety of different types of experience and seeing that it makes some difference. Of course, we like the labels with the X's if we get our choice instead of getting unlabeled data. But we found that there were conditions where the unlabeled data was genuinely useful if we're willing to make certain assumptions, like the co-training assumption or whatever assumption EM is making when it uses the unlabeled data. Did you ever think about it? So why does EM work? I mean, unlabeled data shouldn't really help you learn a function, right? We used EM to train a naive Bayes classifier. We're saying, oh, we can just show X points and not bother to tell you the label Y. And if you use EM, that'll help you somehow convert those unlabeled data points into more information about the function you're learning. If you think about that, it's really not a reasonable thing to think that unlabeled data will help you learn some function from X to Y. All I'm showing you is X's. It can only help you if you're willing to make some assumption that happens to be true of the data. So in the case of EM, what is that assumption generically? In the case of naive Bayes, what is that assumption? Right. So in naive Bayes, it's really the assumption that we know the parametric form of P of X comma Y. Right? And in particular, in the case of naive Bayes, that that parametric form satisfies some conditional independence assumptions, right? But more generically, we talked about using EM for any Bayes net, not just naive Bayes, which is a particular kind of Bayes net. So, you know, and again, I think it's fair to say EM then can have unlabeled data help us, even if it isn't a naive Bayes net. But it will really only help us if the structure of the Bayes net that we write down happens actually, that the world actually agrees that that's the structure it's going to follow when it's giving us the data. And of course, if it doesn't follow that structure, then there's no reason to think that unlabeled data is going to particularly help us. So I think, you know, for me, that's one of the kind of really intriguing things about one of the key intriguing things that we saw in the course was just the fact that unlabeled data can be useful at all for learning functions, and then kind of drilling down to try to understand when and why, and when not. We talked about, once we got the idea that we could think of learning as an optimization problem, we really ran with it, right? So, and then we started talking about a whole bunch of different. Can I write on this? I don't think so. We started talking about a whole bunch of different objective functions that we might optimize. And you should certainly recognize all these from the course. You know, we talked about, well, if we're trying to learn some vector of parameters theta for something like logistic regression or naive Bayes or whatever it is that we're learning, what's the criterion by which we want to pick the values for those parameters? And we talked about, well, let's maximize the probability. Let's pick the parameters that make the observed data most probable, maximum likelihood. Or let's flip it around and pick the parameters that are most probable given the data But to do that, we have to make some modeling assumption, like put a prior on the parameters. And then we get map estimates instead. When we talked about support vector machines, we replaced the whole idea of maximum likelihood by just maximizing the margin. It's a different criterion. But then we saw there was this kind of intriguing similarity between the loss functions for maximizing the margin. Remember that hinge loss? How does that look from your perspective? Hinge loss versus the loss function for logistic regression, which even though it was derived from conditional likelihood, actually had some similarities. We talked about sum of squared errors, which at first sounds like a very ad hoc thing, but then we showed that there was a probabilistic model for regression under which sum of squared error minimization equals maximizing the likelihood. Remember that? Where we said, what if we assume the y values are produced from the x's by some deterministic function, and then we add zero mean Gaussian noise to the result? That probabilistic model, if we then solve for maximum likelihood, tells us that what we should do is equivalent to minimizing the sum of squared errors, which is a very cool idea. And that's a kind of theme also in the field, I would say, is that if people make up some more efficiently solvable objective function, like minimizing the sum of squared errors, then they like to try to justify it in terms of what is the corresponding probabilistic model under which that new objective function would be equivalent to maximum likelihood or maximum conditional likelihood or maximum a posteriori. Because deep down we kind of like the idea of having these probabilistic models because it gives us some understanding of what we're really trying to optimize and maybe conditions under which it's really going to work. Overfitting. I'll tell you now, I've been holding this back, but I was very disappointed at the midterm with the number of people who did not get the right answer on a question that I thought was trivial. I can't write on this, but you'll surely remember this, what I thought was easy, but obviously most people got this question wrong. Remember that overfitting curve for decision trees where you grow the complexity of the decision tree, and as you allow more and more nodes into the decision tree, the training error, of course, keeps reducing. The accuracy on the training set of the decision tree keeps rising. But on a separate test set, as you grow the tree, first the accuracy on the test set rises, but then it falls. You're getting overfitting. And I asked this question on the midterm because I thought this will be an easy one, and then most people got it wrong, it turned out. About what would happen if we just had, I think the question was, what if we had an infinite amount of data? What would happen to these curves? And many people did not get the right answer, which is, of course, if we have more data, we'll have more or less overfitting. Less overfitting, right. If we have, overfitting is especially problematic when we have scarce data. If we have more data, we'll have less overfitting. What is overfitting? Overfitting is really the distance between those two curves. It's the difference between the error you're going to get in the training set and the error you're going to get in truth. And our test set is an unbiased estimate of the true error. So it's really the distance between those curves is the degree of overfitting. And if we had infinite data, we won't have any overfitting. In fact, the two curves just become the same curve. The training one, unfortunately, drops because you can't achieve that high training accuracy by not overfitting. So the training curve will drop, but the test curve will do better. In fact, you expect every time you add more data, the test accuracy should get better because you should be actually learning better. So what happens in that case, two curves come together. So anyway, be sure you understand about overfitting and ways we have of dealing with it, right? So we talked about putting priors on parameters as a way of overfitting. Talked about pack learning as a way of essentially characterizing how bad can the test error be if the training error was only epsilon, or if the training error was 0, we said first. Basically, pack learning was our attempt to bound the difference between the training error and the test error. Bayes networks, that was a big deal. It still is a big deal for us because it gave us a language, a vocabulary for talking about machine learning algorithms that cut across several algorithms. Right? We can draw Bayes nets for hidden Markov models, for Markov decision processes, for naive Bayes. And we realize that every one of those Bayes nets carries with it some set of conditional independence assumptions. We know about deseparation as a way of reading those off. So the nice thing about Bayes nets is it's kind of this generic language for talking about probabilistic models that allowed us to see correspondences between algorithms that otherwise might have looked very different. Hidden Markov models and Bayes nets, or naive Bayes. Sounds different, but just variations on that. And then when we talked about EM, we could talk about EM generically for Bayes nets, and then see that we could use that for training, say, hidden Markov models if we had only partially observed data. Also, we could use EM to train naive Bayes if we had only partially observed data. So it gave us this nice general language. Classification. I don't know what to say about this. We talked about an awful lot of classification algorithms. I think what's interesting there is just what are the dimensions? Why did we talk about so many classification algorithms? Why isn't there just one that we use? Right? And we did talk in the course to some degree about why, right? For example, we talked about, one of my favorites was we talked about naive Bayes and logistic regression as kind of two sides of the same coin. Naive Bayes was this generative probabilistic model that essentially involves training a Bayes net to learn the joint distribution on x sub i's and y. Then we use that to calculate p of y given x. Whereas logistic regression, we really just only model p of y given x directly instead of the joint distribution on x and y. And then we talked about, why might you want to do one versus the other? If you have a lot of data, maybe logistic regression. If you have a little bit of data, maybe naive Bayes, because it's making these conditional independence assumptions which allow it to converge more quickly on the estimates of its parameters. So I would say, to be honest about the field, we don't have a nice clean theory of the relationship between all these different classification methods. But you know and I know that there are kind of sweet spots for different ones of these algorithms in terms of the Venn diagram of all possible applications. Even something like, if you think about decision trees versus neural networks, if I ask you, which I won't now because I'm asking that. I won't ask it on the final. But if I did say, I want you to train a function where the input is an image, a photograph, and the output is a label, yes or no, is this an outdoor scene? Would you use A, neural network, or B, decision tree? Let's take a vote. How many would use neural network? How many would use decision tree? Okay. I would use a neural network. Why? Because think about what decision trees do. They, first, the feature of the problem that seems to me the key one here is images have a lot of pixels. I'm going to give you a high-res picture. It's going to have 1 million pixels. No, from my cell phone, it's going to have 5 million pixels or something. Okay, a high-res picture. Now, those are the features. How deep is how is your decision tree going to how is your decision tree even going to represent a tree that distinguishes outdoor from indoor pictures? Well, maybe there will be blue dots in the top of the picture indicating that there's sky. But
So
that's...
you have to use those direct features.
I'm sorry, I didn't say that's right. Okay, that's fair. Okay, so if I do ask that question on the test and you say, well, you didn't tell us we had to use pixels. But if you do have to use pixels, then I would go with a neural network. Why? Because the neural network is going to take all of those pixels into consideration when it makes its classification. Whereas what the decision tree is going to do is it's going to pick one pixel at the root of the tree and test its value. Based on the value of that one pixel, it's going to go down this way or that way, or maybe 5 different ways, depending on how we discretize it. And then it's going to pick another pixel. And it's going to be really tired by the time it's probably not even going to look at all 5 million pixels. So you see, so there are differences. And one of the difference I was highlighting there was the difference between decision trees as an algorithm that tend to be really good if you have many features and only a few matter, because they'll pick those features and they'll put them in the tree and they'll ignore the others, versus a neural network which is going to use all those features and give them all some weight. Of course, it can give weights of 0 if, in principle. But, you know, and if something like a photograph, probably most of the pixels are potentially relevant. So for that reason, I'd probably go for a neural net. Anyway, you can think about those kind of things. We talked about regression, which is just really classification with real valued output instead of discrete. And, oh, importantly, we talked about kernel regression. One of the really very cool things, you have to admit, because that was, kernel regression was the thing that allowed us to get away with linear algebra by using kernel functions that correspond to operating in some very higher dimensional space where everything is linear, but instead doing all of our computations in the original space. And that really is a good idea. It's widely used. So we're going to run out of time, and I have to leave. My wife has told me I have to leave for the airport right after class, and I'll be in trouble if I don't. So we're going to end on time. Anyway, I hope you got something out of the course. I enjoyed everything so far, and I'm sure I'm going to enjoy the rest, including the poster session. So I'll see you Tuesday for the poster session. And check our website for details on that. But, you know, basically bring a poster. The TAs and I will be around. Subsets of us will grade you. And you should be prepared with, let's say, a 3-minute talk telling us your problem, your approach, and your solution and your conclusions. 3 minutes. And try to practice that because, sadly, with so many posters, we're going to have to move on after 5. And if you take all 5, we won't get to ask any questions. Okay, see you Tuesday. Thank you.